Let's start with this numerical 6. This question is asked in June 2016. The question with respect to unit 9 and 10, and it's from Nuclei. Let's solve this. The activity of radioactive substance is 4700 per minute. So activity, let me represent it as n is equal to 4700 per minute. 5 minutes later, so t is equal to 5 minutes. 5 minutes later, the activity is 2700 per minute. So n, let us say this is initial, that is n naught, and this is 2700 per minute after 5 minutes. Find the decay constant, that is lambda, and half-life of radioactive substance. So if you calculate the decay constant, then we can easily calculate the half-life. So by looking at the quantities n naught, t, n, lambda, we have the direct equation. N is equal to n naught e to the power minus lambda t. The sample after a certain interval of time, sample initial, lambda decay constant, time for the change in sample. So here, let's rearrange this equation. So what happens is n by n naught is equal to e to the power minus lambda t, or we can write it as taking reciprocal n naught by n will be equal to e to the power lambda t. Let's proceed. Taking log on both sides, that is log of n naught by n, which is equal to lambda t. So finally I need lambda. Lambda is equal to 1 over t. This is, we have to convert it to base 10, that is 2.303 log the base 10, 4700 divided by 2700. Okay. So this is 1 by 5 into 2.303. This becomes log 10 and 4700 divided by 2700 becomes 1.74. Taking log of this answer, it's coming out to be, okay, let it almost at 2.303 by 5 into 0.24. So let's solve this. This is 1 by 2.303 divided by 5. We get it as 0.11. 0.11. Lambda, that is per minute. Let's find out we are done with the decay constant. Half-life we need to find out. Let's see. You know the direct formula, half-life is equal to 0.693 divided by the decay constant, which is lambda, and finally I get t half is equal to 0.693 divided by 0.11. So 0.693 divided by 0.11 becomes 6.3. It's coming out to be 6.3 minutes. So you can also convert it into seconds by multiplying with 60. So you can get the answer, or you can stop it there. So we calculated the values of decay constant and also the half-life of radioactive substance. Let's move on to the next question. Let's move on to the question number 8 from the two units, last 2 units, that is unit 9 and 10. This question is from atoms. Sorry, nuclei. A very simple one. Calculate the binding energy and binding energy per nucleon of an oxygen nucleus O16-8 using the following data. Okay, they have given mass of proton, mass of neutron, and mass of the actual mass of the oxygen nucleus. So binding energy is delta m multiplied by square of the speed of light. Delta m, that is mass defect. Delta m is called mass defect and is defined as the difference in the mass between the sum of the constituents of mass of nucleus and the actual mass of the nucleus. That is delta m mass defect ZMP plus A minus ZMN. So this is the mass of the constituents minus the given the actual mass of the nucleus. Let's find out this. Z oxygen 16-8, so Z is 8. Mass of protons, that is multiplied by 1.007825 U. So it is same for all the mass is taken in atomic mass unit here. So that's why I don't write U here. So A minus Z, that is number of neutrons. So the number of neutrons is again A minus Z is 8. So that is 8 multiplied by 1.008665 minus the given mass 15.995. So let's find out this. So 8 into 1.007825, 8.0626 plus 8 multiplied by 1.008665, 8.06932 minus 15.995. So let's solve this. Okay, on solving this, we get 0.13692 U, that is atomic mass unit. Delta M is equal to. So we got delta M. Let's find out this binding energy. One conversion we should remember here is that in order to find out the values in mega electron volt, see one atomic mass unit is equal to 931.5 mega electron volt divided by C square. So here we want to substitute the value 3 into 10 to the power 8 whole square. We substitute this value 1 U in here and let's see. So the binding energy, that is delta M 0.13692 into 931.5 mega electron volt divided by C square, that is in place of U multiplied by C square. This value gets cancelled out. So we get finally as 127.54 mega electron volt. This is binding energy. Okay, so we calculated the binding energy 127.54. And still we need to calculate the binding energy per nuclear. This can also be called as specific binding energy, which is equal to binding energy by the constituents of nucleus, that is the sum of protons and neutrons. So binding energy is 127.54 divided by 16. 127.54 divided by 16, that is total number of neutrons and protons. So we get 7.97 mega electron volt, that is binding energy per nucleon. We get it as 7.97 mega electron volt. So this completes the numerical. It's a very simple one, direct one. We need to calculate the binding energy and binding energy per nucleon. So by calculating the mass defect, you can easily calculate the two quantities. This one you should remember. Okay. So let's proceed for the next numerical. The last 2 units, unit 9 and 10. This question is from dual nature of radiation and matter. A bit lengthy one, but easy. We can make use of Einstein's photoelectric effect. Let's see. The light of frequency 8.41 into 10 to the power 14 Hertz is incident on the metal surface. So this frequency is incident. So I can write it as mu. Incident frequency as mu, that is 8.41 into 10 to the power 14 Hertz. Okay. When it incident on the metal surface, electrons with their maximum speed. So electrons with their maximum speed. So there is V max, write it as Vm. Maximum speed, that is 7.5 into 10 to the power 5 meter per second are ejected from the surface. Calculate the threshold frequency. So the electrons are ejected with this speed. So we need to calculate the threshold frequency of photo emission of electrons. Also find the work function of the metal. So work function is represented by phi naught. So we need to find out the work function. If we are able to find out mu naught, phi naught can be easily found. Find the work function of the metal in electron volt. So this should be in electron volt. Okay. And given H is equal to 6.625 into 10 to the power minus 34 joule second, that is Planck's constant, and mass of the electron. So let's find out the first mu naught. Here the photoelectric process is happening. So what we can do is we can make use of Einstein's photoelectric equation. So what we have, K max is equal to E minus phi naught. K max is equal to E minus phi naught. So phi naught we need to find still. So let's take this on this side, K max on that side. So phi naught is equal to E minus K max. So either we find mu naught, then phi naught, or mu naught, phi naught, then mu naught. No problem. So let's find out phi naught, the work function. Then we can able to find out the frequency. Here we go by bit. First, we'll find out the E, that is energy of incident radiation. Then K max, that is kinetic energy maximum. So let's start with E. E is equal to H mu. H is 6.625 into 10 to the power minus 34 and 8.41 into 10 to the power 14 Hertz. So let's find out. 6.625 multiplied by 8.41. So we get 55.71, or you can take 72 10 to the power minus 34 plus 14 is coming out to be 10 to the power minus 20 joules. This is in joules. You can also convert this one into electron volts by dividing the value by 1.6 into 10 to the power minus 19 joules. So let's convert this one into electron volts. That is 55.72 into 10 to the power minus 20 all divided by 1.6 into 10 to the power minus 19. So we get 34.82 into 10 to the power minus 20 plus 90, that is minus 1. I can write 3.482 electron volt. So this is the energy associated with the incident photon. Okay, let's move on to calculate the K max, that is half m V max square. Half m V max square. So this is going to be half 0.5 multiplied by 9.1 into 10 to the power minus 34 into speed 7.5. So this value is coming out to be, okay, K max is 1 by 2 into mass of electron 9.1 into 10 to the power minus 31 and 7.5 into 10 to the power 5 whole square. So on solving this, we get 255.94 into 10 to the power minus 21 minus 31 10 to the power 5 whole square 10 to the power 10 minus 31 plus 10 is going to be minus 21. So let's convert this one into electron volt, because I need the phi naught finally in terms of electron volt. I already have energy, incident energy in electron volt. Now this is in joules. We need to convert this one into electron volt. So K max is equal to, I write it as 255.94 into 10 to the power minus 21 all divided by 1.6 into 10 to the power minus 19. So we get 159.96 into 10 to the power minus 21 plus 90, that is minus 2. So I can write it as 1.59 or approximately we can take it as 1.6 electron volt. 1.6 electron volt. So this is K max. So we got E and also K max. Let's find out phi naught. It's going to be 3.482 minus 1.6 electron volt. I'm directly writing with respect to this formula. 3.482 minus 1.6. This is coming out to be 1.882 electron volt. 1.882 electron volt. So let's calculate this threshold frequency. So here I have calculated first the work function. What's the relation we have? Phi naught is equal to h mu naught. This implies mu naught is equal to phi divided by h. So this is 1.882 electron volt divided by 6.625 into 10 to the power minus 34. Okay, it's becoming a bit lengthy. Mu naught electron volt, let's convert it into the usual one, joules, by multiplying 1.6 dividing it by 6.625, so we get as 0.454 into, so I have converted 1.882 into joules, that is 3.0112 into 10 to the power minus 19. So minus 34 shifted upwards. So minus 19 plus 34. Get as 15. This is 10 to the power 15. Mu naught is 4.54 into 10 to the power 14 hertz. So this is the final required value of incident frequency. So as I said, it's a bit lengthy but easily solvable. It is depending upon the Einstein's